Good afternoon, everybody. Thanks for joining us today. It is just after 2, so you give it like half a minute or so for a couple more people to come along, and then we'll get started. Um, yeah, looks like we've already got quite a lot of people that have come along and signed up, so that's great. Few more seem to be trickling in. So I think in the interest of time, we'll kick off. So just to quickly introduce everything for today. So for those of you that haven't met me before, my name is Alex Oliver. I'm the partnerships lead for the REWIRE Innovation and Knowledge Centre. And just, yeah, thank you for coming and joining us today for our June 2026 webinar, which is all on vertical GaN technology. I'm going to introduce Matt Smith, our speaker, in a second, but just a couple bits of housekeeping. Firstly, we're going to be recording the session. I think it's already on, and it will be posted online on our YouTube page. So if you want to watch it back, you're available. You can do that. We are going to come to Q&A and questions at the end. We should have about sort of 10 minutes for that. So if you've got any questions, feel free to use either the chat or the Q&A function. I'll be monitoring that throughout, and I'll be prompting bits as well throughout that. I think that's all the housekeeping bits for me. So yeah, I'm just going to quickly introduce Matt to everyone, and then I'll be handing over to him to run through today's webinar. So Dr. Matthew Smith is a senior lecturer and researcher at the University of Bristol with expertise in wide and ultra-wide bandgap material growth, device design, fabrication, and characterization. He's a member of the Center for Device Thermography and Reliability, or CDTR, and he co-leads power electronic device research with Professor Martin Kubel. His research specifically focuses on the development of novel materials and devices for power electronic applications, with projects developing advanced power diodes and transistors based on wide and ultra-wide bandgap materials. Dr. Smith was the 2022 Toshiba Fellow with his research into normally off power transistors leading to world-leading mobility values, and he's also worked on RF power transistor design, front and back-end fabrication, and transistors for space applications. And he is one of our core REWIRE academics as well. So I'm now going to hand over to Matt to start with the webinar.
Excellent. Thank you very much, Alex. And hello, welcome everyone to this REWIRE webinar on vertical GaN. I'm going to share my screen now. Hopefully that's visible. I'll assume it is.
Yeah, all good.
Great, thanks, Alex. Yeah, so thanks for the introduction. I'll dive straight in. Excited to talk to you all today. First of all, going to make the case for vertical GaN devices. So why vertical GaN, why power devices? And then look at some of the devices we've developed here at Bristol. So firstly, focusing on our GaN on GaN devices. I'll get to what that means in a while. So transistors and diodes, and then towards the end, looking at our GaN on silicon technologies as well, and why they're advantageous and some of the potential drawbacks to those. So why gallium nitride for power devices? So gallium nitride's got a lot of very interesting properties. So it's a wide bandgap semiconductor, so 3.4 electron volts compared to just 1.1 for silicon. As a result of that, it's got a very high critical electric field, so the electric field that it can sustain before it breaks down, before it experiences dielectric breakdown, and that's about 10 times higher than silicon. So it's naturally a very attractive material for power electronics. And compared to some of its wide bandgap semiconductor competitors, it's got some nice properties like high electron mobility, even in the bulk phase, not just the 2-deg. It's got high electron mobility and high saturation velocity as well. So lots of other interesting properties, but for power electronics, that's really the ones that jump out. So if we think about where that leaves GaN in terms of applications, we can focus really on these high operating frequency and still modest, relatively high power devices. So we're thinking about data centers, thinking about consumer electronics, and that's in contrast to silicon carbide, which is another wide bandgap semiconductor technology that has advantages over silicon, which is more advantageous in the low frequency regime. So these applications like fast charging infrastructure, renewable energy, industrial and aerospace, that's where gallium nitride really shines. So if we think of a specific application for a GaN power device, we can think about this switch mode power converter. So if we were to convert to DC voltages, so maybe we've got 1 voltage in, voltage out, and how do we do that? Well, we can use a transformer or a linear regulator where we just drop voltage across 2 resistors in series, but both of those options are inherently inefficient. So we're losing energy during this DC-DC voltage conversion process. So they also tend to be quite bulky and limited in their application there. So the alternative to that is to use a switch mode power supply. So this type of power converter here has got some passive components. So we've got capacitors and inductors, and then we've got our active devices that make the core of this. So transistor and a diode. And actually what happens is these devices are switching on and off very quickly. So kilohertz, megahertz type of switching speeds. So even though we're talking about DC-DC power conversion here, the devices are actually switching relatively quickly. And that chops this DC input into these pulses, and then the inductors and the capacitors smooth them out. So if we want to achieve very high efficiency in our voltage conversion, our DC-DC conversion, to do that we need efficient devices. So we need efficient transistors and diodes. That means they're not losing energy when they're switching on and off, and in those on and off states they're not losing energy as well. So very important that we have these efficient devices, these components, if we want to make efficient power converters. So let's think about what we mean by an efficient power device. Well, in the on state, so first of all, for a power device we need to be able to switch it on and off. When it's on, we want it to be ideally 0 resistance. It's never going to be 0, but we want it to be as low resistance as possible. So again, we're not wasting energy as heat when it's on. We want it to be very low resistance when it's switched off. So we do have some leakage current, but we want that to be as low as possible. And crucially, we want it to withstand a very high voltage. So in an application like this kind of power supply, this will be rated to a particular voltage, and we need that device to be able to withstand a voltage when in the off state corresponds to that. And then we also generally want it to be small, so light and low volume, small area. More important for some applications than others, but generally very important. We don't want it to heat up, so again, that's to do with low resistance. And we want it to be fast and efficient when it's switching between these 2 states. So fast generally is quite well related to efficient, so we don't want to be losing energy when we're switching. And we want all of these things to be stable and reliable. So there's no point us making a really high performance device and then after a few cycles it degrades. We need it to be stable under many repeating cycles and also reliable under adverse conditions. So, okay, why gallium nitride then? So that's kind of setting the scene for power devices, but why GaN? Well, I mentioned we've got this application voltage, so a device will have to withstand a certain voltage in one of these power converters, and we can define the breakdown voltage, which is how much voltage we can apply before the semiconductor material in our device breaks down. So very crudely, we've got this model here where the breakdown voltage is defined by the dimensions, so the length over which we're applying voltage, and this property, the critical electric field of the material. So we can increase our breakdown voltage by increasing this value D here. So we've now got a greater distance over which we're dropping the voltage. So that does increase our breakdown voltage, but it does so at the expense of efficiency. So now in the on state, our carriers have got further to travel, so our resistance is increased. So what we really want to do is look for materials with higher critical electric field. So where gallium nitride comes in, for example, where we've got 10 times the critical electric field than we do in silicon. So that's the good news in the on-state and off-state trade-off. Critical electric field is advantageous. And actually, gallium nitride has these other benefits as well. So I mentioned mobility, saturation velocity earlier. So how quickly the carriers move through the material, that's very important because it means as we're opening and closing our channel, so we're essentially charging and discharging our gate capacitor, it means the carriers are able to move more quickly through the device. That's what these numbers here, mobility and saturation velocity, essentially represent. So how quickly the carriers move, really important for how quickly we can switch on and off our devices. and how efficient that process is as well. And it actually has an additional benefit. So the faster we can switch these devices on and off, then the smaller we can make these additional components in our circuit. So if we think about this power converter, it's typically a plastic box, and actually most of the size is taken up by these passive components. And if we can switch these devices on and off even quicker, these devices get smaller, so the whole system shrinks. So gallium nitride compared to silicon has these dual advantages where it's got a higher critical electric field and higher speed of its carriers in the mobility and the saturation velocity. So that's the case for gallium nitride. So a little bit about where GaN came from, and what I'm going to talk a bit later about is vertical GaN. So how do we get to vertical GaN? We have to start with lateral GaN. So gallium nitride high electron mobility transistors, or HEMTs, they came on the scene around early 2000s. So the way these things work is we've got gallium nitride layer, and then we've got a thin layer of aluminium gallium nitride, and actually all our charge carriers are localized to this interface. So we have something called a two-dimensional electron gas. It's called a 2-deg. So unlike most devices where we have this bulk conduction where charge is moving all through the device, in this case the charge is localized very close to the surface in this 2-deg layer. So this occurs due to a conduction band offset in the AlGaN and GaN, and also something called polarization or charge polarization at the interface gives us this effect. And it's a very positive effect because this thin sheet of charge is very mobile, so it acts as a channel for transistors. So we're passing current from source to drain, and we're controlling the flow of current using our gate electrode here. So with just a few volts on the gate, we can deplete the 2-deg underneath in this region here and turn our transistor on and off. So it's still a very growing market, but these devices are really focused on the RF market, so switching at kind of gigahertz levels, still at high power, but not really focused on power devices. The reason for that is essentially because they're normally on. So we have this 2-deg that exists, and we have to apply a gate bias to turn that 2-deg off. So what that means is our threshold voltage, so the voltage, the gate voltage at which the device turns off, is less than 0. So if our gate fails, if our gate driver circuit was to fail, then the device would be on, and that's not good from a power device perspective because you leave your load, your system at risk of power surges there. So what people did was introduce this p-type GaN layer underneath the gate. So it's a very similar structure, the GaN power device, lateral GaN power devices, but we're able to achieve this enhancement mode operation where now our threshold voltage is greater than 0. So now if our gate fails, the device is off, and actually we have to apply a gate voltage to turn the device on. That's achieved by this p-GaN layer, which depletes the 2-deg through a PN junction here. So actually when we apply a gate bias, we put the gate into forward bias, we reduce our depletion region, and the device turns on. So very similar to the HEMT structure, but just with this additional layer here, this p-GaN layer. And we can see at 0 volts, it's raised the conduction band above the Fermi level, so it's normally off, protects the load if the gate driver fails. So that's good, and there are some very positive numbers for the market in terms of GaN power devices. Commercial devices still based on this p-GaN gated HEMT structure. There are some alternative structures as well. So something I worked on at Toshiba, where we etch away the 2-deg and make a MOSFET, a recessed gate MOSFET. It's another option. So both of these devices based on the HEMT platform, but with some augmentations. They have some drawbacks, but they both work pretty well, and it is a very growing market. But both of these are lateral devices still. So let's dig in a little bit more on how these lateral devices work. So actually, that's what I've shown so far, where we've got this GaN channel and the AlGaN barrier layer, and then maybe something on top to make it enhancement mode. But actually what we have is a lot more going on down here. So we've got our substrate, which is typically silicon or maybe silicon carbide, sapphire, depending on whether we're focused on power RF devices. But in order to grow our high quality gallium nitride channel, we have to do lots of things between the substrate and the channel. So we have these nucleation and strain relief layers, which can be several microns, and they're defective, resistive, so they're essentially magical layers, we can think of them as, that alleviate strain and account for the mechanical and thermal differences between the gallium nitride and the substrate. So that's non-native substrates. So yeah, again, typically silicon's used for power devices, which is great for production costs because silicon is very cheap. So conduction is along the surface in these lateral devices, and that's perpendicular to these things' dislocations. So when we grow this gallium nitride layer on these non-native substrates, we get something called dislocations in our structure, which are extended defects in the crystal, and they're essentially misalignment of atoms, and they point vertically towards the surface like that. So they're going up, down, well, from the substrate towards the surface, but our channel is perpendicular. Our conduction of this 2-deg is perpendicular to those dislocations. So they tend not to have too much of an impact on device performance. They do have a bit of an impact, but we can get away with a relatively high dislocation density because our 2-deg is perpendicular to them. And in terms of how much breakdown voltage we can achieve, so remember, breakdown voltage is a really important metric here. That scales with the distance between the gate and the drain. So if we increase this gate drain distance, then we increase the breakdown voltage. And again, that's coming at the cost of on-state resistance. But crucially here, when we increase this distance, we reduce the amount of devices we can fit on the chip. We're reducing our amount of power per unit area because this is scaling with the area of the device. And actually, this also increases capacitance. So usually when we make 2 electrodes further apart, capacitance goes down. But due to all the field plates and coupling between the 2-deg and the gate in these devices, actually capacitance increases as we go towards 1 kilovolt. So contrast that with vertical GaN devices, where now we've got a gallium nitride substrate, which is very expensive, but it means we've got now much higher quality gallium nitride epitaxial material. So our dislocation density is much less. And this time we're conducting vertically through the structure. So parallel to our dislocations, but we've got a lot less dislocations because we're on gallium nitride substrates. So the electric field peak is still between our gate and drain. So it's still this distance here. But now we increase the breakdown voltage by increasing the thickness of our device. So rather than having to increase the area on the chip, we can just increase the thickness of the epi layer. So more devices per unit area, which has positive cost implications. And actually, the capacitance also decreases as we increase our gate drain distance. So we have this favorable scaling between breakdown voltage and capacitance in these devices. So for kilovolt class power devices, which particularly for AI data centers and some other really important emerging applications, that's really important because it means we've got positive scaling of our breakdown voltage with capacitance. It means we've got more devices per unit area, which again for AI data centers is very important. It means we can get more, less power devices are needed per space on the rack. And smaller passives as well, because this lower capacitance means we can switch everything faster. So these capacitors and inductors in our power circuit, they're reducing in size as well. So higher power density at kilovolt class ranges is really why we're so interested in these vertical GaN devices. So there are lots of different types of vertical GaN transistors. Highlighted what they all have in common here typically is that they all use these gallium nitride substrates. They've all got a source on the top and a drain on the bottom, but then how that gate actually works, there's a few options there. So these are just a few different designs. We focus on FinFETs here at Bristol. Each design has its advantage, but we think this is the best. We've got this dual gate control and no P-type layer, which has certain drawbacks. And this is just to highlight that companies have really started to pay attention to vertical GaN. So onsemi recently revealed vertical GaN product line. Got the vertical semiconductor company as well, raising a lot of money. Going to bring out products soon. So, okay, how do we actually make these vertical GaN devices in Bristol? Well, we start with our GaN-on-GaN epitaxial structure. This is work by my student Chengji Zhang. So during his PhD, He's writing up at the moment, but his task was to essentially develop a process for these devices based on previous work by Thomas Palacios, Yuhao Zhang in MIT. So based on their papers, we developed this process where we start with this GaN-on-GaN material, working with Dynex semiconductors here, and make the fin, deposit our dielectric, deposit our gates, do this photoresist etch back process, very challenging. Enables us to expose the top of the fin and then etch the molybdenum gate, etch away the dielectric, and then make our source contact, and then finally metallize the drain. So it's a very complicated process flow. This is underselling the complicated nature of it actually, and lots of things we have to control for here. So the fin width, for example, the fin depth, all the angles in this case, very important, have big impact on device performance. So this was our first generation design, and lots of process debugging that Chengji went through to achieve this. So we can see micro masking effects here as we're trying to make the fin. Lots of process development until we finally have these nice parallel fins, high quality. This etch back process, very non-trivial, so trying to find a photoresist and an annealing and an etch process which just nicely exposes the top of the fin, and very challenging. Opening the source, very, very difficult. So these fins tend to be sub-micron, maybe 1 micron, and then we have to open a gap in a dielectric layer on top of this fin, and that gap you can see here is maybe a few hundred nanometers. So very challenging E-beam lithography alignment here. But yeah, credit to Chengji for doing great work there. So fabricating our devices, we see good news for this first generation is they seem to work quite well in the on state. So we've got something that looks like a transistor characteristic, nice linear ohmic contacts here, and our drain current, or output current, is increasing as we increase our gate bias. Looking at the transfer characteristics, again, confirms we've got reasonable characteristics. We can see the threshold voltage scaling with the fin width, which is what we expect based on our simulations. Reasonable gate current, so not too many problems with gate leakage in the on state. So we simulated these devices in Silvaco Atlas, and Victory recently, and we find that everything works reasonably well. All the device properties scale as they should with things like fin width and fin depth. Yes, we can see here 1 micron, 700 nanometers, and 500 nanometer gates, and that threshold voltage becoming more positive as we reduce our fin width, because we've got better gate control, which is really important from a power device perspective. Drawbacks there is we squeeze our fin, so as we make our fin smaller, our current goes down. Again, that's what we expect because we've got less area for our current to flow through. So the bad news for this first generation was that they're very low breakdown voltage, so breaking down at somewhere like 30 volts. So for a power device, that's not good. We want to be up in the hundreds of volts or the thousands of volts, something like that. So we saw this catastrophic breakdown, non-recoverable dielectric breakdown, and what we think here is that it was breaking down in this essentially capacitor at the base of the fin there. So we looked at these miscap test structures. So alongside the devices, we fabricate test structures on the chip, and we find that actually they have a fairly similar breakdown voltage and seems to be a similar mechanism as well. So it's a bit of a clue that that's what's going on there. So the next step, again, based on the team from MIT's designs, was to include this spacer layer. So second generation devices now, we've got this additional silicon nitride spacer layer here at the base of the fin. So all this work was recently published in IEEE Transactions on Electron Devices, put the DOI there. So the second generation devices on state, they look very, very similar to the first generation. So adding this silicon nitride spacer layer didn't degrade our on-state properties. That's good news. But it massively enhanced our off-state properties. So we can see first generation breakdown, as we saw, it's sort of 30 volts kind of range. Second generation breakdown voltage, similar breakdown mechanism. It's this dielectric breakdown through the base of the fin, but we can see the breakdown voltage here is around 1 kilovolt. So something like a 30-35 times improvement when we add this silicon nitride spacer layer. And again, we confirmed that using our miscap test structures. So one thing we did look at was, why do we see such a big increase in breakdown voltage when all we've done is we've basically increased the thickness of our dielectric by about 6 times, and we see somewhere between a 30 and 35 times increase in breakdown voltage. So you would expect a linear scaling if it was just a case of the dielectric layer redistributing the electric field. So what we found was the fixed charge distribution in these layers is very important, which wasn't previously reported. So what we did was model fixed charge purely at interfaces here. That's not necessarily the case, but if we localize fixed charge here, it gives us a chance to model it and get some numbers out. So first of all, we looked at this generation 1 device. So we got this miscap test structure. We can use simulations. Again, this is a Silvaco simulation to find the band diagram when we have 0 fixed charge and some non-zero amount of fixed charge. We can see how that changes our band diagram here. And what we can actually do is look at our experimental flat band voltage and our experimental breakdown voltage and find this value of fixed charge at this interface. So quite straightforward there for this structure. For this structure, we have 2 interfaces, so we've got 2 parameters to play with here. So turns out we can have lots of configurations of these 2 fixed charge numbers that give us results that are consistent with our flat band capacitance, but only one configuration that's consistent with both our breakdown voltage and our flat band voltage, and that's this configuration here where we have negative charge at this interface and positive charge at this interface. So what that's actually doing, it's introducing an electric field inside our dielectrics. So as we add the fixed charge at the interfaces, negative charge here brings these bands up, positive charge brings these bands down. So we get this electric field. And what actually happens is that electric field is built into the device because of that fixed charge. So when we apply a bias on our device, the electric field that's resulting from the applied bias has to fight against this built-in electric field in the device. So this is our characteristic, this orange dashed line here. Without the fixed charge, we can see it's breaking down around 100 volts. But when we get this fixed charge configuration here, we have this effect where it's fighting against our electric field initially, and then once it's done that, we're able to achieve this kind of 900, 1000 breakdown voltage. So interesting result. It's not just the device structure, but also the fabrication conditions and the fixed charge distributions that determine the breakdown voltages in these devices. Okay, so once we've made these devices with high breakdown voltage, we looked at stressing them. So this is a characteristic where we have, first of all, just measuring our transfer characteristic in these second generation high breakdown voltage devices, and then we stress them under bias. So this is positive gate bias stress, positive drain bias, and then we remeasure the transfer characteristic intermittently during that stress phase. So what we find here is that initially, this green curve, we get some threshold voltage, but then as we apply bias, that threshold voltage drifts. So here we've got the first generation devices, so without the silicon nitride, and then the second generation devices, these high breakdown voltage devices that have the silicon nitride. And we can see that with stress time, our breakdown voltage, our threshold voltage for those first generation devices, it's quite stable. For those second generation devices, it's all over the place. We get this quite steep increase here. Now, somewhat good news is that it recovers. So if we take that bias away and then look at the recovery time, it does drop back down. It eventually does reach 0. And then we find the same thing when we do a negative bias stress. So negative bias on the gate here, similar story, but except the threshold voltage is moving in the opposite direction. So really strong credit to Chengji here. He put a lot of work in to try and figure out what was actually going on. Really interesting result was that we would maybe expect, there's a mistake here, this should be, this is the second generation design, this is the first generation, but we might expect that adding this silicon nitride spacer layer here, that's what's caused the change in threshold voltage shift. So we might expect that it's trapped charge in this region. That's initially what we suspected. But from simulations, we found out that actually if you include a bunch of fixed charge here, or trapped charge in this region, it doesn't give you this type of characteristic. It just degrades your on current a little bit, because you're essentially squeezing the fin. If you want to have this kind of effect on the threshold voltage, what you need to do is trap charge in this region, so on these side walls of the fins underneath the gate. That's where we're going to get this threshold voltage shift. So what we conclude then is that it's not actually the silicon nitride spacer itself which is causing this degradation, excuse me. It's the process of depositing it and then removing it, which is introducing some defects on this sidewall here. So I won't dwell on this, but Chengji did some great work where he looked at the time constants and the relationship between stress time and threshold voltage, and found we have some tunneling front model where charge tunnels into the aluminium oxide dielectric. But essentially, yeah, same thing for the negative bias. Essentially what we have is this problem where we've deposited our silicon nitride, etched it back using a photoresist etch back process, exposed our fin, and then deposited our aluminium oxide. So this fin region here is damaged by this deposition and possibly also the removal process. So what we did was introduce this third generation device where we try and get the best of both worlds. So now we've still got our spacer layer, it's still present, but the order of our aluminium oxide gate dielectric and our spacer layer has been flipped. So now we deposit our gate dielectric first, then deposit our spacer layer, and then etch it back. So during that silicon nitride spacer layer deposition and etch back process, the sidewall of the fin is protected by the aluminium oxide gate dielectric layer. So in terms of the on-state performance, third generation devices again look very similar. So again, good news, the modifications to the process that we made didn't affect the on-state performance. But if we look at our, and then if we look at our off-state performance, so breakdown voltage, there is a slight drop here. So we're at 750 compared to sort of 950, 1000 here. So possibly a slight reduction associated with this process. But in terms of our stability, it's really, really enhanced compared to those generation 2 devices. So we can see here the generation 3 is basically mapping on top of those generation 1 devices. So when we stress the devices, they're not degrading in the same way as those generation 2 devices were. So this plot summarizes that. So in terms of breakdown voltage, generation 1 to generation 2, we saw this huge jump, but we also saw this big jump in the threshold voltage drift. So we saw degradation in our stability. And with these generation 3 devices where we've changed the order of our process, we're essentially able to maintain the best of both. So we've got the high performance in this high breakdown voltage, and we've got this high stability now in this small threshold voltage shift under stress. Okay, so that's our work on FinFETs, transistors. Looking back at this power converter circuit, another element that's important is diodes. So we've also been looking at Schottky barrier diodes, again using this GaN on GaN platform. And all this work in collaboration with Dynex Semiconductors, so thanks a lot to Dynex for this. So initially we looked at just planar Schottky barrier diodes, so just cathode on the back of our doped substrate, and then an anode contact on the top. And we found our on-state performance was reasonable, off-state performance not great, breaking down at around 200 volts. So we applied this edge termination technique, and I'll come on to what that means and why that's important in a couple of slides. But essentially what we're doing here is we're introducing this MESA, we call it, so this kind of table shape here. And we played around with some of these parameters. So the spacing between the edge of the MESA and our anode contact, and also the depth of the MESA as well. So again, good news in the on-state, changing things around up here didn't really have an effect on our on current. Looks fairly similar between the two devices. Slight drop when we apply the MESA edge termination because we've reduced the current density slightly, but that's reasonably, it's fairly negligible. Both these devices have a quite low turn-on voltage, reasonably consistent with what we expect from the work function and the semiconductor properties. And here we can see the range of values that we get when we apply MESA edge termination in terms of our breakdown voltage. So this black line here is our planar device, so this one over here. So we apply voltage in reverse bias, it's breaking down around 200 volts. But when we apply this MESA edge termination with these different T MESA and D MESA values, we can see we definitely increase our breakdown voltage, and how much we increase it depends on what the dimensions of these numbers are. So this is summarizing that plot. We've got our planar device over here. So this is our MESA anode separation. It's T MESA on the x-axis here. And these different symbols represent different MESA depths. So as we decrease our MESA anode separation, we can see a sudden increase in our breakdown voltage. So that's this parameter here. As we're making the anode and the MESA edge closer together, we increase the effectiveness of our MESA edge termination. So what's actually going on? Well, we can see from this series of structure files from Silvaco, this is the electric field at the anode edge here. So this is where the electric field peaks. And as we reduce this value T MESA, so again, as we make the MESA edge closer to our anode contact, we're suppressing this peak in the electric field close to the anode. So this is what we mean by edge termination. So whenever we have a contact in a device, the electric field's going to peak at the edge of the contact. So we need to find a way in semiconductor devices to terminate the edges such that we suppress this electric field peak. And what we're showing here is that MESA edge termination is an effective way of doing that. And this value T MESA is really quite important, and it's not something that's reported currently. So we do find that the devices do still break down at the edge. So this is without any edge termination. This is with good high breakdown voltage MESA edge termination. So we can still see the devices exploding around the edge of the devices here. So it suggests that we can optimize it further. We still do have a peak in the electric field at the edge, but our breakdown voltages clearly show an improvement. And yeah, again, simulation shows why that is. So actually, when we do simulate these devices, we find that compared to our experimental data, so experimental data is these solid lines here, and now we've got MESA depth on the x-axis. It should be the case that as we keep going deeper, since we make our MESA deeper and deeper, we should still see an increase. We should keep seeing an increase in our breakdown voltage. What we find experimentally is that saturates somewhere between 1 and 2 microns of our MESA depth. And we don't see that in simulation. So why is that? Well, we looked at these devices in SEM, and what we find is that for the deeper MESA structures, so 1 micron and 2 micron depths, we have these features around the edge of our MESAs here. So this is the anode contact, this is the MESA, and then this is the MESA floor. So as we go deeper to sort of 1 and 2 micron depth, we can see these features here, and these are sharp, irregular features which are going to be electric field spikes in their own right. So they're what's going to cause this this early breakdown. And what's actually happening here is when we're making the MESA structure, we use a nickel hard mask. So as we're etching, nickel can redeposit on the surface. So during the plasma etch process, this nickel's not entirely stable, it can redeposit. And then those redeposits, they act as what we call micro masks. So a bit of nickel's on the surface there, and it's actually masking more of the gallium nitride. So when we strip the nickel mask, we have these additional features which we don't want. And in some cases, they attach themselves to the MESA edge and cause this these problems here. So yeah, we've shown that MESA edge termination is an effective way to enhance the breakdown voltage, and it improves our off-state performance without degrading the on-state performance. We've shown how critical it is to consider the geometry. And what we note is that MESA edge termination is typically used in combination with other edge termination techniques, so field plating and dielectric deposition, that kind of thing. So this is by no means a cap on performance here, but we hope to see this type of understanding applied as a component of these more advanced MESA edge termination techniques. Okay, so for the next few minutes, I'm going to talk about our work on GaN on silicon. So I mentioned earlier that for vertical GaN devices, we work on these gallium nitride substrates. So that's necessary, or so the thinking goes, to reduce our dislocation density, because now the current path is vertical in these vertical devices. Current path is in the same direction as our dislocations. So we need to minimize the amount of dislocations by using gallium nitride substrates. Problem there is that from a cost perspective, I don't necessarily believe these numbers, but it's from this reference here. Certainly the scaling is accurate. We see much higher cost per area for GaN on GaN compared to GaN on silicon. So if we could achieve vertical GaN on silicon devices with good performance, that certainly would have a huge cost benefit. So if we think about dislocations, then I've drawn them as kind of gray lines here. It's much worse in our GaN on silicon layer compared to GaN on GaN. And we have the added complication that when we're on a silicon substrate, we have all these additional layers that I mentioned earlier. So we've not just got our substrate, but we've got microns potentially of stream relief layers that we have to somehow manage. So we can't just deposit our drain contact on the backside. We have to etch through our silicon substrate, etch through our silicon as our stream relief layers, and then stop on our embedded N+ GaN layer in order to achieve something like a vertical device in this GaN on silicon. So in terms of material quality, GaN on GaN has around 10 to the 6 dislocations per centimeter squared, can go down even to 10 to the 4. GaN on silicon somewhere around the 10 to the 9 region, so about 1,000 times more dislocations per area in GaN on silicon that we have to contend with. An additional complication here for GaN on silicon is the thickness that we can grow. So GaN on GaN, when we grow GaN on a GaN substrate, cool it back down to room temperature, everything's expanding and contracting at the same rate because GaN has the same thermal conductivity as the GaN substrate. That's not the case for GaN on silicon. So that's part of the job of all these stream relief layers, is to manage that. But ultimately it means that we're limited in how thick we can grow in terms of gallium nitride on these non-native substrates. So we gave it a go. This is material supplied by University of Cambridge, Professor Rachel Oliver's group. So we have about a micron thick of our UID drift layer. That's a typo, it should be 1 micron. And we have this subdrift layer here where the aim is to annihilate as many dislocations as we can in this region and then make this region as higher quality as possible. So reducing the dislocations in this region by playing tricks in the growth and trying to annihilate dislocations down here. So what we found was that we can control the dislocation density in the drift layer through the growth conditions. So this is the ammonia pre-dose time. It's how long we expose this substrate to ammonia for. We can see a dip in the dislocation density at some fixed value. So we made devices using these structures. These are quasi-vertical devices. So earlier I said you have to etch through the substrate and all these layers here. To get around doing that initially, we'd make these quasi-vertical devices where the current path is vertical, but we put our cathode to the side here off a MESA. So we do have quite poor turn-on characteristics here in these quasi-vertical devices. That's still under investigation. We think we know the reason, but we're currently working to investigate that. In terms of our breakdown voltage, though, we do see quite a range. So this is that fairly well optimized GaN on GaN device with the MESA edge termination, and these are our GaN on silicon structures here. So breakdown all the way from kind of sub 50 volts up to around 150 volts. And what we find is that there is reasonable scaling with dislocation density. So as we reduce our dislocation density, our breakdown voltage goes up, which is what we would expect. So for those low dislocation density samples, we find that the devices are breaking down at the edge, similar to what we saw in our GaN on GaN devices, suggesting we're limited by edge termination here. For these high dislocation density samples, actually they break down not at the edge, but the breakdown seems to be aligned with these pits that we see in the surface. So probably these pits are acting as current paths, and we're seeing maybe some thermal effects here where the device is breaking down early. Now, interestingly, if we look at the device simulation here, bearing in mind that for our GaN on GaN devices, we have a much thicker epi layer. We do have a much higher breakdown voltage, but accounting for the thickness of the epi layer, what we find is that the electric field at the Schottky interface for GaN on GaN compared to GaN on silicon is not that different. It's something in the kind of 10–20% range. Now, this simulation isn't perfect. It doesn't account for edge termination differences, which is something that we're working on. But it would seem to suggest that despite the 1,000 times higher dislocation density that we have in GaN on silicon, we don't see 1,000 times decrease in our breakdown, in our critical electric field. It seems to be relatively stable there. And again, it tends to suggest that the more important limitation for GaN on silicon is thickness, is how thick we can grow these layers. Although, of course, earlier we did see that there is an effect of dislocations, but if we can achieve relatively high quality material, if we can grow thick material, then you should be able to achieve relatively high breakdown voltage in vertical GaN on silicon devices. And in fact, people have shown that in the last sort of 5 years. There's the GaN project in Europe, others, Japan and elsewhere, that show reasonably high quality and high breakdown voltage GaN on silicon vertical devices. So it's a very promising area for the future, bearing in mind there's a much reduced cost for GaN on silicon compared to GaN on GaN. So that breakdown voltage effect, dislocation density isn't the full story. What we do find is that there are some outliers, and we also have to consider wafer bow. So this story isn't fully told. I think we still have some more investigations to do here on the relationship between dislocation density, breakdown voltage, growth conditions before we can fully understand this. But we're currently fabricating devices which we hope are going to shed some light on that. Okay, so we want to move eventually to fully vertical devices, skipping through here just for time. We did make FinFET based on the GaN on silicon platform, quasi-vertical, so again, putting the drain contact to the side rather than etching all the way through. Reasonable on-state performance, very low breakdown voltage. We think we might know the reasons for that. This was done actually before the GaN on GaN FinFET work I showed earlier. So we think we have our next generation of these GaN on silicon FinFETs should be much higher breakdown voltage. But yeah, they were breaking down at kind of 30 volts initially. And again, our next step is to make these fully vertical devices. So similar to what others have done, etch through this silicon substrate, etch through our strain relief layers, and then stop on our embedded GaN layer here. This is very non-trivial. So this is several hundreds of microns thick. This is several microns thick. This is a few hundred nanometers. So stopping on this 200 nanometer thick layer is going to be quite challenging. We have made some progress there, so we're able to etch through the silicon and stop on the GaN quite nicely. But yeah, this is ongoing work, so watch this space. Great, and that brings me to my conclusion. So hope I've shown that vertical devices can offer very efficient power handling for high currents, high voltages, for cooler, lighter systems, some really important emerging applications where they should really make some commercial headway. We've shown GaN on GaN devices, this first, second, and third generation, where we can improve performance, so maintain our on and off state properties, and also achieve high reliability through optimization of our device design and fabrication. And then a little snippet into potentially the low cost future for vertical GaN, where we can look at non-native substrates. So controlling the dislocation density in GaN on silicon and moving towards high breakdown voltage GaN on silicon vertical devices. So thank you very much to all the CDTR team and all the REWIRE team as well, and also to Dynex, who funded the vertical GaN on GaN work. Yeah, thanks to everyone I work with, particularly Chengji Zhang and Ritanjay Kumar, PhD student and postdoc, who've done the bulk of the work that I've shown today. So thanks to them, and happy to answer any questions.
Great, thanks very much for that, Matt. That was really, really interesting. So yeah, as Matt said, we've now got some time for questions. If anybody has any, feel free to put them in the chat or the Q&A, and we can come to them. I can read them out for you. I've got a couple to start with, Matt, whilst other people are putting some in. So it's one of the last slides you were talking about this, the non-trivial backside etch that you're going to have to do for the GaN on silicon FinFETs. How how applicable is that kind of for putting it into processes when you're thinking about sort of scaling that kind of developing that technology and putting it into real world production? Is that something that is easily applicable into those kinds of environments?
Yeah, I think it should be. I mean, this silicon deep etch process is the Bosch process, which has been around for a while. It's what we use, so it's quite well established. In terms of, we tend to, well, so far we've worked with single fin devices. So if you want to scale the current up, one thing we can do is increase the length of these fins. So out of the page, we can increase the length, and there's really no limit to that. But we want to add fins in parallel. So we'd need to make our aperture at the bottom here a little bit wider, but actually we tend to make it a lot wider anyway. You can see the dimensions here. This is sort of on the centimeter scale, even sort of quite large areas here. We make them nice and circular. So I don't really see a fundamental limitation there. The challenge is going to be when I've made these types of structures in the past that you can maybe kind of see it here. The gallium nitride, the nitride membrane that's left behind when you etch is quite high stress, so it's bowed like this. So controlling that can be quite challenging. And actually, maybe a major drawback is going to be thermal effects. So how do we handle the large amounts of heat that are associated with the high currents that we get as we're passing things vertically? So there are ways that can be managed, certainly lots of ideas, things to try, but I know that's certainly a concern that when these sort of membrane devices were explored a few years ago, that was a big limitation that they came across.
Great. And then another one around the process development side of things. So you've like with the GaN on GaN technology, you've basically got the first, second, and third generation. How long is it typically taking to develop one of those processes, and how much does it speed up on the second and third generation when you've obviously got those sort of initial learnings from the first ones, the ones that preceded it?
Yeah, definitely the first one's the longest one because you have to get that baseline down initially. And the second generation, we were still essentially following the work from Thomas Palacios's group in MIT. So in terms of design, that wasn't too tricky, but optimizing the processes, that was, I showed earlier some slides right on the like the resist etch back process, that kind of thing. That is quite challenging. Certainly as we move to higher density multi-fin devices, that's going to be more challenging again. But all just essentially an engineering challenge. The third generation was less of an issue, I would say, because it was relatively small changes to the design, just flipping that layer. That was more kind of inspiration from Chengji's side to realize that actually, it's important to protect the fin during that process. So yeah, it varies depending on where we are in the production cycle, I suppose.
Great, thanks, Matt. So I've had a couple come in. So one from Jonathan, actually two from Jonathan. So thanks, Matt. Is the GaN FinFET a surface or bulk conduction device? And do you see any mobility degradation with the Gen 2 devices with the surface exposed to the nitride etch? And what sort of mobilities are you achieving?
Yeah, great question. So it's a bulk conduction device. It's all going through the fin and then down through the layer here, through our bulk drift layer. In terms of mobility degradation, there probably is some. So if I go back to those schematics, if my slides are going to let me, it's difficult to say because the measuring the mobility on those fin sidewalls is quite tricky. And in fact, measuring any property directly on these fin sidewalls is quite tricky. So we can model them and we can look at the changing output current, which seems to be minimal. So it suggests it's certainly not a showstopper. But actually the yes, this is the first generation output current, not much difference within statistical variation actually. So there may be a bit of a drop in mobility as a result of these processes, but the contribution, there was a paper from Thomas Palacios' group a few years ago which showed the contribution to the total resistance of the device from this fin is, if I recall, it's in the sort of 5-10% area. So any changes to mobility here are fairly negligible, which to be honest is a shame because there's a lot of interesting things you can do in this region in terms of optimizing the mobility there. But yeah, it does look like the major drawbacks from this first and second generation were trapping effects and stability rather than on-state performance. So yeah, I can't tell the exact mobility there, John, but one thing we are doing is try to develop test structures which can help us to extract properties of these fin sidewalls directly. Yeah, maybe we can talk more about that offline.
Great. One from Akil. So thanks. Would the breakdown in the vertical diodes improve using slanted edge termination instead of a step profile?
Yeah, good question, Akil. So probably it would, and in fact, there's a lot of papers that show simulations that show yes, it would. But anyone who's ever tried to etch a slanted profile will tell you how challenging it can be. You know, you see these nice simulation papers which say if you change the angle by 10 degrees, you get this factor of improvement. But it's a lot easier simulated than fabricated in my experience. So short answer, yes. But I think more effectively, combining the MESA edge termination with other edge termination techniques is probably the way to go. So guard rings potentially, I mean, if you do that, you lose the benefit of the small T MESA. But certainly field plates and dielectric layers, there's nothing stopping us combining those with the MESA edge termination, and potentially a slant as well.
Great. We've got a couple more. So Akinori's said, thanks for the nice presentation. I was wondering if you've compared between GaN on GaN and GaN on silicon devices at higher temperature. High temperature measurement might be able to be more clearly might be able to more clearly compare the effect of dislocation density.
Yeah, absolutely. It's a great suggestion. So we have looked at that. Something we're working on currently is trying to understand what are the physical mechanisms that underpin, or how important are dislocations. We can kind of see from just the performance, but why? What are the physical mechanisms that underpin that? Measuring at high temperature is certainly a useful tool there because most transport mechanisms, leakage mechanisms, have a signature with temperature. So that's absolutely something that we have done and continue to do, and hopefully we can publish something soon on certainly the GaN on silicon devices with the dislocation densities, and benchmarking them against GaN on GaN is a good idea.
Great. So Pallavi has asked, what was the mobility for the vertical GaN FinFET, as etching the fin will degrade the mobility?
Yeah, similar to John's question earlier, I think, isn't it? It's if we just look at the IDVG characteristics, transfer characteristics on screen here, it looks like we've not seen too much of a degradation when we include this spacer layer, which we know has an effect on the fin sidewall by our trapping effects, the drift in the threshold voltage. So measuring the mobility directly is very challenging in these vertical devices. We can't make a nice hole measurement structure that's going to tell us mobility in the lateral direction, not the vertical direction. But what we can say is these modifications that we're making to improve performance don't really seem to affect mobility that much.
Great. I think final question. So it's from Abdul Fatai. So how sensitive is the BV to the MESA sidewall angle, and where does the BV actually initiate? So the MESA edge or the bulk GaN?
Yes, again, I think I sort of covered that one in response to Akil's question, but it is sensitive to the sidewall angle. It's also going to be sensitive to the rounding at the base of the MESA here. So depending on the conditions, if we have a very small T MESA, then actually we start to see a peak in this region in simulation. But actually smoothing that corner out's very common practice using a sort of wet etch after a dry etch fabrication process. So all of these things, little tweaks to these designs we can do to have measurable and significant impacts on breakdown voltage. So maybe we can follow up if we're looking for some specific numbers there. But yeah, thanks for the question.
Great, thank you. We've now hit 3 o'clock, so I think we're going to close up there. Massive thank you to you, Matt, for a great presentation. And if anyone has any follow-up questions, you can feel free to get in touch with myself or Matt by email. A couple final bits of housekeeping that I've put into the chat. So if you want to collaborate on future webinars, feel free to get in touch. We're more than happy to look at opportunities for that. so long as it looks at power semiconductors, power electronics, semiconductors in general. Feel free to get in touch. Our next webinar is actually taking place in 4 weeks' time. We're doing that in collaboration with the April AI Hub, led by the University of Edinburgh, looking at the importance of AI for discovering new electronic materials for things like power electronics. So if you want to sign up, the link is in the chat as well. But yeah, thank you to everyone who has attended today. I hope you found it really interesting. I know I have. And again, thank you again to Matt, our speaker, for a really great presentation. And yeah, enjoy the rest of your afternoon, everyone.
Thanks, Alex. Thanks, everyone. Bye.
Bye.